Hello. This lecture will cover pages 49 of my lecture notes. Please print that page out and have it in front of you as I present this lecture on Nodal Analysis, Chapter 3b, Nodal Analysis with Dependent Current Sources and Voltage Sources. If you look at page 49, we're going to talk about nodal analysis with dependent current sources, starting out with E3.4 and E3.5. They're in your textbook, but here's E3.4, and I want you to notice here that we're going to do nodal analysis, but we have a current source here. We have a current-controlled current source in the network, and all it's going to do is add a third equation. I mean, it's just like what we've been doing. If you take a look at your procedure on how to solve nodal problems with nodal analysis, we have our ground reference here. I label currents. The author is giving you I.O., but here's I.O. out here. This is where they have labeled I.O. It's in this branch here, plus to minus. This is a 4 milliamp source. I labeled a current I1 up here, left to right, put a plus to minus in. And I labeled a current out here, I2, plus to minus. And I saw three nodes. One of the nodes is a reference node, so I need two equations here. Okay, so I need an equation called this V1. This is all node V1. Here's node V2. So if you take a look down here, this should be pretty straightforward for you. You want to find V1 and V2 in this problem. Note at node V1 by Kirchhoff's current law. Start up here, write this first equation, then make sure you go to this second equation. Okay, don't forget, when we're talking in this case about current I1, it's a negative current because it's leaving this node, but it's negative. Make sure you put these parentheses in. If you don't, you'll forget to distribute this minus sign, and you divide by 10. That's the current I1 up here. And then you want to find the least common denominator. I found 10K. Clean this up and get the system equation here. This is not the final equation I'd expect on exam, but in the interest of time, I got you this far. At node V2 by Kirchhoff's current law, you write a node equation right here. Using Kirchhoff's current law, you end up with this equation. Make sure you understand it. You clean it up by getting a least common denominator, 10K, and multiplying both sides by 10K. Throw it into your calculator, or throw it in your iPhone or your smartphone. But notice here, you're going to have two equations with three unknowns here. Why? Because I.O. is in the equation up here. Because of that dependent source. Remember what I told you here. That you're going to need one extra equation for every dependent source you have. We have one dependent source, so we need one extra equation for that controlling variable. So I just say by inspection, what is I.O.? What is I.O.? Well, I.O. is the current out here. We already wrote it up here. Right there it is. It's I.O. So if you understood, you know, how we got, I'm sorry. We, on the second step up here, we would have put in I.O. We didn't do it because I didn't show you the next equation here, but down here, what is I.O.? Well, I.O. is simply equal to V1 minus 0 divided by 10K. It's just V1 over 10K. There's the third equation you need. You can either substitute and then solve these simultaneously, or get all three of these in a standard form, 3 by 3 determinant, if you will. And then you can calculate V1 as 16 volts and V2 is minus 8 volts. That's example E3.4. Example 3.5 looks like that. Notice I have the voltage controlled current source up here. Three nodes, 1, 2, and 3. This right here is already given as Vx. This was given as Vx in the problem. That's what the author says. That's Vx. You could have called this V1, but don't call that V1. It would be a dummy variable. It's already labeled as Vout. The author gave you that. So the Vx was already defined in this problem, if you could find it. And here's Vout. There's the two node voltages. I assign currents with the passive direction. I put I1. I didn't have to assign a current here because they give it to you. Don't have to assign a current here because they give it to you. but currents I had to assign here, I2 and I3. At node Vx by Kirchhoff's current law, there's the first equation. I'll give you credit for that. And then you go down to here. Then least common denominator is 6k. Clean it all up and get the system equation. At node V out by Kirchhoff's current law, out here, you can write this equation. Make the one step farther. Least common denominator is 12k. There's two equations with three unknowns. Why? Because we have one dependent source, and you're going to need a third equation. You're going to need a third equation for that Vx. By inspection, what is V sub x? Okay. Well, V sub x turns out to be equal to the voltage right there. They gave it to you. It's Vx. And we know Vx is equal to the current times that resistance. If this is a ground reference and we already know this is I1, the voltage at this point has to be 3K times I1. That's Ohm's law. And then solve the equations through substitution or whatever technique you need. V out is 4 volts. And that's that problem. E3.7 and E3.8, I'm going to point those out real quick to you. These are problems you should be able to, if you can do problems like this, you'll have no trouble on the exam or the quiz. I mean, notice here, use nodal analysis to find I out in the network. I assign two currents. Okay. I didn't have to make this a node here. You could call that V1 and that V2 if you want to, but why call that V1 whenever that voltage is 6 volts? Don't put variables in you don't need. If this is ground and you're up 6 volts, that's 6 volts right there. You already know that point. So that's not a node we need to write an equation at. Same thing over here. If this is ground and you're up 3 volts, you're plus 3. Now if this is turned around, this would be minus 3 up here. But it's plus 3. So at node V0 by Kirchhoff's, there's two nodes and one's a reference. So right there, you just need one equation. And there's your equation right there. There's the current equation at that point when I assign the currents. There's your second step. What is I1? What's the current I1? It's the voltage here minus the voltage here divided by 6K. That's a 6K. What's I out? It's the voltage here minus the voltage here divided by 3K. And what's I2 in the direction I assigned it? It's the voltage here minus the voltage here divided by 6K equals 0. Least common denominator 6K, clean it up, and you end up with IO is equal to 0.75 milliamps. That's a 5-minute problem. If it takes you any longer than 5 minutes to work this problem, you're going to be behind in the quizzes and the exams. Make sure you can do it that quick. Down here, E3.8, I want you to notice, how do I set this up? Well, that is a current source. It's not a voltage source like up here, so I have to label that node V1 because I don't know the voltage there, like I knew it up here because it was a voltage source. That's V1, there's V2, there's V out. Author gave that. Sign currents, write 3 equations. Solve the equations. V out, this voltage here is 3.89 volts. And then finally, I want to look at nodal analysis with voltage sources. Voltage sources in nodal analysis presents us with a little bit of a problem. And you're going to see why as we look over a couple examples and look over some of these problems down here. There's example 3.6 and 3.7 in the book. And I want you to notice here example 3.6. And it tells you, if you're looking over example 3.6, the problem you run into. Well, I'm going to explain it to you because look over here. When we're working this problem out and we try to write a node equation at that point for currents, how are you going to get the current there? Notice and look back through all of our other problems we just worked with nodal analysis. Okay? In all the cases, that if a particular branch was involved, and it was not referenced to ground. It was referenced up here. It was a current source, and you knew the current. Here, there's no way of getting that current directly. There's no way of writing an equation for that current up here right now. There's no way of doing it. So what you have to do is you have to tie that together. What you end up doing in these problems, it's called a super node. You circle that and you make that one big node. And then you just write your equations from currents here, currents here, currents here, and currents here. But keep it in mind that these are related directly. In this case right here, can you look at that and see that V1 is simply equal to V2 plus 6. If you're at V2 and you add 6 volts to it, you get V1. V1 is equal to V2 plus 6. That's going to be an equation we're going to use when we solve the problems. Or if you want to say V2, if you want to write an equation, V2 is equal to what? Well, V2 is equal to V1 minus 6. Either equation's accurate and it would work in solving these problems. Same thing down here, supernode. So these two nodes are tied together through a common voltage, so that ties them directly together with that voltage. So the equation you're going to get down here is, what's V3 equal to? Well, V3 down here is going to be equal to, well, this node down here, whatever this node, well, what they did is they called this node up here, let's do this. Let's call this VA up here. Yeah, let's call that VA. And what's VA going to be if this is V3? Well, VA, don't even look up. VA is going to be V3 plus 12 volts. That ties these together directly. Now, we're going to use that in these problems as you go through these problems. It's called supernodes. So, I want to see problem 3.9, E39. Looks like this. Notice that this is not a current source. It's a supernode. And I labeled all the currents here. I labeled current I1 because we didn't know it. This is a voltage source here. That's I1. This is a current source. You don't have to do that because you know what the current is. The current will be the same the whole way to this point. Resistor wouldn't make any difference. You know the current. But that's a voltage source. So we don't know the current there. 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 So you can call this V1 if you want. Call this V2. Call this V3. Call this V4. There are 1, 2, 3, 4, 5 nodes. But look, one of these is a reference node is 0 volts. And by inspection, V1 is 6 volts if this is a reference. And V4 is minus 4 volts. So by inspection, don't start sticking in some variables you don't need. V1 is 6 volts and V4 is minus 4 volts. Okay. Well, if you want to run with the voltages as variables, some students do. So let me keep them in for just a minute. At the supernode, at this supernode, let's tie these voltages together. Just a little bit of thoughts. By inspection, you can take a look and see V3 is equal to V2 plus 12. You're going to use that equation shortly. And now, at the supernode, all you do is circle this node and just treat it as a big gray cloud. We have a current coming in, and we have a current gone out, we have a current gone out, we have a current gone out. That's just one big node. Forget about what's inside it. So at the supernode, by Kirchhoff's current law, we have, you look up here, and notice you have a plus I1 coming in, a minus I2 coming out, a minus I0 coming out, the author gave you that, and a minus I4 coming out, equals 0. If you take a look, what is I1? I1 is equal to, I assigned the current in this direction, so this is the more positive. It's V1 minus V2. That's where you use this now. V1 minus V2 over 2K. What is I2? I2 is V2 minus 0 over 1K. What's V3? V3, what is I-O. I'm sorry. What is I-O? I-O is V3 minus 0 over 2K. And then finally, what is I4? I4 is, this is the more positive. I'm not practicing what I preach. I want to put a plus in there. I want to put a minus in there. So I4 is V3 minus V4 all over 2K ohms. Well, what I did was, if you take a look, you can come down and least common denominator 2K. I cleaned this all up. I got this equation. You can see that V2, and I made the substitutions up here. This is where I just put them in. You could have done it earlier, but V1 is 6 volts, V4 is minus 4 volts, and you get V2 is equal to a minus 4.4 volts. Therefore, what's V3? Well, V3, we already found out up here, was equal to V. Look up there. Look at the top. What's V3? It's V2 plus 12. That's 7.6 volts. So if V3 is 7.6 volts, you can find I/O, and that's what they wanted you to find in the problem. Once you find this voltage, you divide it by the 2K, and you get 3.8 milliamps. 310 in the book looks like this. And let's take a look to see what we want to look at here, what we want to look at next. Yeah, let's look at this. Notice my super node there. You have to recognize there's, you can't find a current in this direction. That's the trouble it gives you into when you find voltage sources that aren't referenced to ground. If this was a voltage source here of 8 volts, V1 would be 8 volts. But it's not. It's a current source. So you have to put a V1 there. And there's your super node right there. So you can write the equation, what is V2 in terms of V1? So you get rid of one of these variables. V2 is equal to V1 plus 12. Then you write your current equation, current coming in here, current gone out here, current gone out here, current gone out there, and current gone out there. You have two equations to write. One at the super node and one at V out. And you solve it, V out is 5.6 volts. E311, very popular problem. There's another problem. Notice it's not a current source, so you have to make one big super node out of that. So if you make one big super node and you assign currents, there's a current already there. You have to assign that one. The author gives you, that's IX. There's 2 milliamps given. Treat that as a cloud at the node, the super node by Kirchhoff's current law. There's current coming in, current going out, current gone out, current gone out equals 0. Well, what is V? What is IX? IX is V1 minus 0 over 2K. What's I/O going to be? Well, I/O is going to be V2 minus 0 over 2K. And by inspection, you can see how's V2 and V1 related to one another. V2 is just equal to V1 plus this guy, plus 2000 IX. And we already know IX is V1 over 2K. Make a substitution in up here. You just substitute to find V1. V2 is equal to 2 VI, or V1. If you just look up here, when you look at these equations, you'll see this. And when you know V2, you can find I/O. When you know V2, you can find I/O. 1.3333 milliamps. 1.333 milliamps. And finally, E312. E312. Let's see what we have. Yeah, nice problem too for you to look at. find VO using nodal analysis. And all I did in this problem here was I assign currents, put in my passive sign convention. I recognize that I have a supernode there. There's a supernode right here. But notice this is a dependent source. I'm going to wrap this up in 1 minute here, this lecture, but this is an important part of it. Take a look at this circuit. A couple things I can draw to your attention. This is one of the more harder problems, but once you see this, it's a 10-minute problem. That supernode right there allows you to just write one nodal equation right at that point. Treat that as a cloud. Okay, and you're going to have this current coming in. You're going to have this current going out. You're going to have this current going out, this current going out, and this current, just for the heck of it, I assigned it, well, the author assigned it right to left, just to mix things up. Right to left. That current's coming in. It's going to be a positive current coming into this. There's your IX. So you're going to have one equation at that supernode. You're going to have another equation at this node V out, because that's V out. I just called it V out. There's your two equations. And then you're going to need two more equations. Well, there's a lot of equations, but not really. One equation is V1 is equal to V2 plus 4KIX. What's V1 in terms of V2 to eliminate that? Well, if you're at V2, you add 4KIX to get to V1. Once you see this supernode stuff, it's pretty easy. And then the only other expression you need is, you know, there's a dependent source in this. Every dependent source you see requires one more equation. You have to find an equation for the controlling variable IX. Look at this circuit. IX goes from here to here. The author assigns it from right to left. What is that current? It's just Ohm's law. IX in this 2K ohm resistor is V out, the more positive side. That's why this convention is so important. I'm going to stop saying that. I think you got the idea. It's pretty damn important. But V out minus V2 divided by 2K. That's IX. And you have everything you need to solve that. That's about as much information as I can give you on nodal analysis. It is extremely important when you start modeling active devices in later courses. And if you can just get the system equations. I've had students call me and say, Professor Skip, I can get these system equations and they're easy. I can get system equations for anything and I just plug it into my calculator and I can get the answers. A lot of students can't get it. I want you to be one of the students that call me and say, you know what? That nodal stuff's pretty easy. But you have to work out these problems and you have to watch this video a second time if you have to. Very important concept is nodal analysis. And that concludes this lecture.